Good evening, students. Today we will discuss about line defects. Already I have discussed about imperfections in crystal structure. So line defects is a type of crystal imperfection. The main two-dimensional or line defects are dislocations. A dislocation is a linear disturbance of the atomic arrangement of a crystal. Along the line of dislocation, atoms in a solid are arranged anomalously. The crystalline order is restored on either side of a dislocation, but the atoms on one side have moved or slipped. So, line defect is nothing but a linear disturbance of atomic arrangement. So, there is a disturbance. The pattern, the regularity is disturbed. So, what are the causes of line defect or dislocation? Dislocations are generated and move when a stress is applied. So, when a stress is applied, the crystal structure pattern is distorted at a particular point. If this disturbance occurs along a line, then that dislocation is known as line defect. In the previous class, we have discussed about point defects, because at that defect, only at certain point, either vacancy created or interstitial position atom occupies, or certain impurity substituted a regular atom. But in this case, a line defect or defect occurs along a line. So, different types of dislocations are edge dislocation or Taylor or ruin dislocation, and second one is screw dislocation or Burger's dislocation. So, what are the effects of dislocation? Slip occurs due to dislocation, which causes plastic deformation of metals. You have already known what is plastic deformation. Plastic deformation is permanent deformation. So, this deformation occurs due to slip, and slip occurs due to presence of dislocation. Dislocation causes other mechanical phenomena like fatigue, strain hardening, yielding. So, now we will discuss about edge dislocation. There are two types of dislocation. One is edge dislocation and the other one is screw dislocation. So, what is edge dislocation? When within a crystal structure, atoms are removed from a portion of a plane, an edge dislocation occurs at the end of the remaining extra half plane of the atoms. So, we know crystal structure is a three-dimensional regular ordered pattern of atoms. So, from these three dimensions, if from a plane certain atoms are removed, by which the other atoms act as an extra half plane. So, at the edge of this extra half plane, the dislocation or the disturbance or the disorderness of atoms occurs. An edge dislocation is always accompanied by the zones of compression and tension. In edge dislocation, the Burger vector is perpendicular to the direction of dislocation. So this is the figure of dislocation. So here the extra row of atoms, this is extra because from this plane the below atoms were removed. So this causes an extra half plane, and at the edge of this extra half plane the disturbance occurs. So this is another figure where this extra half plane is below two lines. So this is the direction of Burger vector, and this is the direction of dislocation line. So dislocation line is perpendicular to the Burger's vector. So in edge dislocation, the atoms just above the slip plane are in compression, and those just below the slip plane are in tension. So a stress field surrounds this dislocation. When the extra row of atoms is above the slip plane, it is called positive dislocation and is denoted by the sign inverted T. And when the extra row of atom is below the slip plane, it is called negative edge dislocation and is represented by sign T, capital T. So next we will discuss about screw dislocation. So in edge dislocation, the dislocation occurs in a line which is at the edge of the extra half plane, and here the Burger vector is perpendicular to the dislocation line. In screw dislocation, the displacement of atoms occur in two different planes which are mutually at right angles to each other. The lattice points displaced around the dislocation in the lattice follow a helical path, and for this reason this dislocation is known as screw dislocation. So screw dislocation occurs at two different planes which are mutually at right angle to each other, and the dislocation follow a helical path. The line of dislocation follow a helical path. In screw dislocation, the Burger vector lies parallel to the direction of dislocation. So this is the figure of screw dislocation. Here in two different planes the dislocation occurs which are mutually perpendicular, and this is the dislocation line. So in this video we have discussed about edge dislocation and screw dislocation. The both dislocations are line defects and occurs where the atomic structure get disturbed due to application of force or stress. So what are the effects of imperfections on material properties? How it affects? It affects or influences the characteristics of the material like mechanical strength, electrical properties and chemical reactions. The role of imperfections in heat treatment is very important. Imperfections account for crystal growth, diffusion mechanism, annealing and precipitation. Besides this, other metallurgical phenomena such as oxidation, corrosion, yield strength, creep, fatigue and fracture are governed by imperfections. So while discussing heat treatment, we will discuss about this role of imperfections on crystal growth and diffusion mechanism, and annealing and precipitation are a type of heat treatment process. So it will be discussed in detail later, but however, the role of imperfections is of importance for these areas, heat treatment and other metallurgical phenomena. Imperfections are not always harmful to metals. Sometimes they are generated to obtain the desired properties. For example, carbon is added to steel as interstitial impurity to improve the mechanical properties, and these properties are further improved by heat treatment. So imperfections are required to give desired properties and homogeneous structure in metals and their alloys. So in the next video we will discuss about deformation by slip and twinning.